In this video, we will talk about the last of our conjugate distributions, multivariate conjugate distributions, which generalize directly from the univariate case. We will specifically talk about the Dirichlet multinomial, which is a generalization of the beta binomial, and the multivariate Gaussian, which is a generalization of the univariate Gaussian case. Okay, so let's start with the Dirichlet distribution. Remind ourselves what it looks like. If we have k categories and theta I takes on values between 0 and 1, and typically we can think of these as probabilities of a particular category occurring. And this is our random variable, so these theta i's are our random variable. And in this case, we're going to have a vector of them. So we'll have from 1 to k of these theta i's. Then each of the theta i's have a Dirichlet distribution with parameters alpha I 1 to k. And the PDF is as shown with the normalizing constant in front and the kernel, which is the product of the theta i's to the alpha I minus 1. It's the case that the expectation of each one of the theta i's is given by a ratio of the alphas, the particular alpha I. So in other words, if we look at the expectation of theta 1, it's alpha 1 over the summation of all the other alphas. The expectation of theta 2 is alpha 2 over the summation of all the alphas, and so forth. If we let this summation of the alphas be equal to alpha naught, then we can easily write the variance as shown, which is the product of, again, the particular alpha. So for example, if we're looking at the variance for theta 1, it's alpha 1 times the quantity, the summation of all the alphas minus alpha 1. And that divided by, again, the summation squared times the summation plus 1. The Dirichlet, as you may recall, is located on the simplex. So in 3 dimensions, that's an equilateral triangle. And it can take on a variety of different shapes, including this sort of bathtub shape on the simplex, which is when alpha is equal to 0.8, 0.8, 0.8, or some fraction like that. It can also be a totally flat uniform distribution, which is when alpha is equal to all ones. And it can be a distribution which is unimodal, spiked in one particular place. An example here is alpha equals 7, 7, and 7. Or it can be skewed on one side, which is shown with alpha 1 equals 5, alpha 2 equals 2, and alpha 3 equals 1. Okay, so with that review of the Dirichlet, we can now look at the Dirichlet conjugate for a multinomial likelihood. So the multinomial likelihood then, recall, we now have a vector of outcomes, x1 through xk, where this outcome shows the number of times that we see each one of the categories. So for example, a good example of a multinomial is our admission to university. We could either deny someone admission, waitlist them, or accept them for admission. So we have 3 categories. And these x's then would count the number in each one of those categories for n trials. So x1 could count the number of denies, x2 could count the number of waitlists, and x3 could count the number of admissions. And the thetas are the probabilities of those outcomes. So theta 1 would be the probability that an applicant is denied, theta 2, the probability the applicant is waitlisted, and theta 3, the probability the applicant is admitted. So the sum of all of these x's then, and in particular, then, if you think about our example, the number denied, waitlisted, and admitted has to equal the total number of observations that we have. And we see that the multinomial has a kernel, which is just the product of these probabilities taken to the power of the number of times we observe it. So, for example, theta 1, the number of times that we are, the probability that someone is rejected would be taken to the power of the number of times we've observed a rejection for an applicant. And that would be the product for each one of these possible outcomes. Okay, the conjugate prior for this multinomial likelihood is the Dirichlet. And as we just saw in the previous slides, the Dirichlet has a kernel which looks like the product of theta i's to the alpha I minus 1. And so obviously we just take the product of these two as Bayes' rule and divide by the probability of the evidence. Okay, so with a Dirichlet conjugate prior, a multinomial likelihood, we have a posterior which is also Dirichlet. And notice that this Dirichlet has updated parameters. In particular, the parameters have gone from being alpha I to alpha I plus xi, where xi again is the number of observations we have in each one of the categories. Let's now look at the second case, again a straightforward extension of the univariate case, the multivariate Gaussian. So we'll start as we did in the univariate case with an unknown mean and a known variance-covariance matrix. In the univariate case, of course, we just had a variance, but for the multivariate Gaussian, we have a variance-covariance matrix. So we'll let M, capital M, be our mean vector for the likelihood, which is a multivariate Gaussian, in k dimensions. We'll let tau be the precision matrix. And this, as we saw in the univariate case, is just the inverse of the variance. So in this case, it's the matrix which is the inverse of the variance-covariance matrix. And again, that's k by k dimensions. The likelihood then with these n trials, and we'll designate that by what is really a matrix. And the matrix is showing the outcomes on each individual trial of all the variables in this multivariate process. Okay, so an example of this would be our testing example from last time, but instead of having one test, we could have, say, 3 tests. We could consider GRE with a math outcome, a verbal outcome, and an analytics outcome. So those would represent 3 possible outcomes. And each XI, for instance, the first one is student 1, their outcome on each one of those tests. X2 would be student 2, the outcome for that student on each one of those tests, and so forth, all the way up to capital N number of students. And that likelihood then is given by a multivariate Gaussian. The kernel of that Gaussian is shown, which is again a quadratic expression in the exponent of the difference between each value and the mean vector for that multivariate Gaussian. The prior with parameters mu and tau naught, again, we know what the precision is for the likelihood. So since we know the precision for the likelihood, then we have a conditional value here, what amounts to effectively a conditional, because we know the precision. So that means that the prior distribution in this case is a Gaussian, given by the quadratic expression, which is the difference between the mean of the likelihood minus the mean of the prior, which is mu naught, multiplied through the precision matrix, and then again the mean of the likelihood minus the mean of the prior, the mean vector of the prior. Well, if the prior is a Gaussian, this is a conjugate with a Gaussian likelihood, then the posterior is Gaussian. And now the parameters for this, or the parameter for this is updated as the new mu vector as shown. And this mu vector has the same property as we saw in the univariate case, that it will converge to the sample average as n gets large. Okay, let's finally consider the Gaussian case with an unknown mean and an unknown variance-covariance matrix. For notation, we're going to let S be the sum of squared differences between the values that we observe in the data and the sample average. So this is the outer product between these vectors, which gives us the sum of squares, differences between the outcome values and their sample average values. Okay, so for this multivariate Gaussian likelihood, we will use a multivariate Gaussian conditional prior for the mean of that likelihood. This again is a straightforward extension to what we did in the univariate case, except that now we have a multivariate Gaussian likelihood instead of a univariate Gaussian, which means that our Gaussian has a mean vector for a prior parameter, and that's mu naught, and it has a precision parameter, which is given by nu, which is a scalar, times the precision matrix, which is given by the bold W. The nu parameter is very much like tau naught. In the univariate case, we can consider it to be roughly the number of observations we think we have in our prior distribution. And in that sense, it has to be strictly greater than 0. So as we had a gamma distribution for the prior on the variance for the univariate Gaussian, or excuse me, on the precision for the univariate Gaussian, we have a Wishart distribution as the prior distribution on the precision matrix. And this Wishart distribution, recall, is a nice distribution. It's very much like a generalized gamma, except on a matrix as opposed to being on a univariate random variable, which means that we can completely handle the case of this precision matrix. And the Wishart has, very much like the gamma, has two parameters. One parameter, alpha, is the degrees of freedom, and the other parameter, r, and it's bold R, is a precision matrix. The degrees of freedom have to be greater than k minus 1. And recall that k is the number of terms, the number of variables that we have in our likelihood function. So in the case of our testing, it would be 3, the 3 different tests that we had: math, verbal, and analytics. And in this case, we say that alpha has to be greater than 2, which is 3 minus 1. The likelihood, as we said, is a multivariate Gaussian. It has unknown mean vector, capital M, and an unknown precision matrix, capital W. Okay, if this is a conjugate analysis, that conditional Gaussian, multivariate Gaussian prior will yield a posterior, which is multivariate Gaussian, and that's as shown. And the new parameters for this multivariate Gaussian are shown with mu star being the updated mean vector for the posterior multivariate Gaussian, and the nu plus n times the matrix W being the updated precision. The posterior for the precision matrix, again, recall that the prior is Wishart, therefore the posterior is Wishart, again with updated values for its parameters. It now has alpha plus n being the number of observations, degrees of freedom, and a new precision matrix. And this update equation for the precision matrix is very similar to what we saw in the univariate case. In particular, notice that it has the sum of squares term S, and it has the squared difference between the mean of the prior, the conditional prior, and the sample average. So it's very similar to what we saw in the univariate case. Also very similar to what we saw in the univariate case, we can derive the marginal distribution of the mean, knowing that we have a conditional multivariate Gaussian prior for the mean and a Wishart distribution as a prior for the precision. Then we can multiply the two together to get our joint distribution and integrate over the precision. And when we do that integration, we obtain the marginal prior distribution for the mean of the likelihood. And that integration results in a t-distribution. And this t-distribution has alpha minus k plus 1 degrees of freedom, very similar to what we saw in the univariate case, now with the update that we have k parameter values, or k variables in our likelihood function. And the location parameter is identical to the conditional prior for the mean, and the precision also updated now by the values that we're obtaining from our data. So this gives us then the ability to obtain the distribution, the posterior distribution for the mean of the likelihood function. And that is given by, again, a multivariate t because it's conjugate. So the prior was a multivariate t. The conjugate now is a multivariate t. So this conjugate is for the mean vector of the likelihood given the data x, and it has alpha plus n minus k plus 1 degrees of freedom, a location parameter mu star, and given by the posterior distribution, the conditional posterior distribution for the mean, and a new precision matrix, again given by, this time updated by the data. And the data in this case contain the number of observations that we've observed, and we have a new precision matrix, which was given by what we found the precision to be the second parameter in our Wishart distribution, which was this scaling or precision matrix. And that concludes our discussion of conjugate priors. Next time we'll talk about non-informative priors.